Black holes, those massive and frightening objects in deep space that have been so popularized by Hollywood that it's difficult to separate fiction from reality. However, the most powerful space telescope ever, the James Webb Space Telescope, has revealed, for the first time ever, a real image of the inside of a black hole. What exactly did the JWST reveal and how did it achieve this? Stay tuned to find out. Black holes are some of the most amazing and mysterious objects in the universe. They are regions of space where the gravity is so strong that nothing can escape, not even light. They are invisible to our eyes, but we can detect them by their effects on the surrounding matter and radiation. Now, despite how popularized the term is these days, black hole was not used until the 1960s when physicist John Wheeler popularized it in his lectures and writings. Before that, scientists used different names for these objects such as dark stars, frozen stars, or collapsars. And the idea of a star so dense that light could not escape was first proposed by John Michel and Pierre-Simon Laplace in the 18th century based on Newton's theory of gravity. So where exactly do black holes form? Actually, black holes can form in different ways depending on their size and origin. The most common type of black hole is called a stellar black hole, which forms when a massive star runs out of fuel and collapses under its own gravity. This process releases a huge amount of energy and creates a supernova explosion that blows away most of the star's outer layers. But the core of the star remains and it becomes a black hole if it's more than about 3 times the mass of the Sun. So how many black holes are out there in the universe? Well, it's hard to estimate how many black holes there are in the universe because they are very difficult to observe directly. However, based on theoretical models and indirect evidence, scientists think that there are many black holes of different sizes and origins. There may be as many as 100 million stellar black holes in our galaxy alone, and not only that, every large galaxy may have a supermassive black hole at its center. And alongside all of that, there may also be countless primordial and microscopic black holes scattered throughout the cosmos, but we've not yet found any conclusive proof of their existence. When the James Webb Space Telescope launched, scientists knew it was only a matter of time before it started to make discoveries about black holes, and this amazing telescope has been doing just that. With its powerful infrared vision, it can see beyond the dust and gas that obscure the first stars and galaxies that formed after the Big Bang, and among its amazing discoveries, it has found the oldest black hole in the universe, a cosmic monster 10 million times heavier than our Sun. How did JWST find the black hole, though? The black hole is located at the center of a baby galaxy that formed just 570 million years after the Big Bang, when the universe was only about 4% of its current age. This galaxy is so far away that its light has taken 13.2 billion years to reach us, making it one of the most distant objects ever observed. To find this black hole, JWST used 2 of its infrared cameras, the mid-infrared instrument or MIRI and the near-infrared camera or NIRCam. These cameras have built-in spectrographs, which are devices that split light into its component frequencies or colors. By analyzing the spectrum of light from the galaxy, JWST could measure its redshift, which is a measure of how much the light has been stretched by the expansion of the universe. The higher the redshift, the further away and older the object is. The galaxy hosting the black hole has a redshift of 12.5, which means that its light has been stretched by a factor of 13.5 since it was emitted. This is one of the highest redshifts ever measured, and it indicates that JWST is looking at a very early stage of cosmic history. But how did JWST know that there is a black hole at the center of this galaxy? Well, the clue was in the brightness and color of the light. The galaxy is very bright in infrared wavelengths, which means that it's emitting a lot of heat. This heat comes from gas and dust that are falling into a supermassive black hole, forming an accretion disk around it. As the material gets closer to the black hole, it gets hotter and hotter until it emits high-energy radiation such as X-rays and gamma rays. Some of this radiation escapes from the accretion disk, but some of it is absorbed by dust and gas around it, which then re-emit it as infrared radiation. By comparing the brightness and color of the galaxy in different infrared wavelengths, JWST could estimate the mass and temperature of the black hole and its accretion disk. The results showed that the black hole has a mass of about 10 million times that of the Sun, and that its accretion disk has a temperature of about 1 million degrees Celsius, or 1.8 million degrees Fahrenheit. But why is this discovery important? This discovery is important for several reasons. First, it shows that JWST is capable of detecting very faint and distant objects that were previously invisible to other telescopes. This opens up new possibilities for exploring the early universe and learning more about how stars, galaxies, and black holes formed. Second, it challenges our understanding of how supermassive black holes grow and evolve. The existence of such a massive black hole so soon after the Big Bang is puzzling because there was not enough time for it to grow by accreting matter or merging with other black holes. This suggests that there may be other mechanisms or processes that helped create these cosmic monsters in the young universe. Third, it provides clues about how galaxies and black holes influence each other. The galaxy hosting the black hole is very active in star formation, which means that it's converting gas into new stars at a high rate. This may be related to the presence of the black hole, which may trigger or enhance star formation by injecting energy and feedback into its surroundings. Alternatively, star formation may provide fuel for the black hole to grow by feeding it with gas and dust. So what's next after this discovery? Well, this discovery is just one example of what JWST can do with its unprecedented sensitivity and resolution in infrared wavelengths. JWST will continue to observe this galaxy and other candidates for hosting ancient black holes, as well as many other fascinating objects in the early universe. JWST will also study how these objects change over time by taking repeated observations at different epochs. JWST will also collaborate with other telescopes on Earth and in space to get a more complete picture of these objects. For example, JWST will work with X-ray telescopes such as Chandra and XMM Newton to measure the high-energy radiation from black holes, and with radio telescopes such as ALMA and SCAR to measure their jets and outflows. And JWST will also complement other missions that are studying different aspects of cosmic history, such as Planck, WMAP, and Euclid for cosmology, Hubble and Spitzer for galaxy evolution, and TESS and Kepler for exoplanets. But of course, the JWST has much more to offer concerning expanding our knowledge of black holes. And it also detected super strange molecules swirling around supermassive black holes, something that has eluded scientists for decades. These molecules are called polycyclic aromatic hydrocarbons, or PAHs, and they are composed of rings of carbon and hydrogen atoms. PAHs are very common in the universe, and they are found in many places such as interstellar dust, comets, meteorites, and even on Earth. PAHs are important for several reasons. They can be building blocks for life, they can be tracers for star formation, and they can be indicators of environmental pollution. Now, PAHs emit infrared light when they are heated by ultraviolet radiation from stars or other sources. This makes them easy to detect with the JWST's MIRI, which can measure the brightness and color of the infrared light from PAHs. By analyzing the spectrum of the light, JWST can determine the size, shape, and charge of the PAHs as well as their temperature and abundance. So where did JWST find them? JWST found PAHs in the centers of 3 active galaxies, which are galaxies that have supermassive black holes at their cores. These black holes are millions or billions of times more massive than the Sun, and they are surrounded by disks of gas and dust that fall into them. As the material gets closer to the black hole, it gets hotter and brighter, emitting intense radiation across the electromagnetic spectrum. This radiation can also affect the surrounding environment, creating jets, winds, and outflows of matter and energy. The 3 galaxies that JWST studied are NGC 6552, NGC 7319, and NGC 7469, which are located between 200 million and 370 million light-years away from Earth. They are part of a larger sample of active galaxies that JWST is observing as part of a program called AGN MIRI Guaranteed Time Observations, or AMIGO. The goal of this program is to study how supermassive black holes grow and evolve and how they influence their host galaxies. But why is this discovery so surprising? This discovery is surprising because scientists did not expect to find PAHs in the centers of active galaxies. Previous models had predicted that harsh radiation from the supermassive black holes would destroy all PAHs in their vicinity, leaving only atomic or molecular hydrogen behind. However, JWST showed that PAHs are actually abundant in the nuclear regions of these galaxies, indicating that they can survive or form in these extreme conditions. However, JWST also showed that the PAHs in these galaxies are different from those found in other places. The PAHs in these galaxies are larger and neutral, meaning that they have no electric charge. This suggests that the radiation from the supermassive black holes has altered the properties of the PAHs, either by breaking down smaller or charged PAHs or by adding more carbon atoms to them. But what are the implications of this discovery? This discovery has several implications for our understanding of active galaxies and PAHs. First, it shows that JWST is a powerful tool for studying these objects, as it can reveal details that were previously inaccessible by other telescopes. JWST can also observe these objects over time to see how they change and evolve. Second, it challenges our models of how supermassive black holes affect their surroundings. The presence of PAHs in these galaxies implies that there are complex chemical processes happening near the black holes involving gas, dust, and radiation. These processes may have implications for how matter flows into or out of the black holes and how they influence star formation and galaxy evolution. Third, it complicates our use of PAHs as indicators for star formation. PAHs are often used to estimate how much star formation is happening in a galaxy based on their infrared emission. However, if PAHs can also be produced or modified by supermassive black holes, then their emission may not reflect only star formation but also other factors. Fourth, it raises questions about the role of PAHs as potential building blocks for life. PAHs are considered to be important precursors for more complex organic molecules that may be involved in life processes. However, if PAHs can survive or form in harsh environments near supermassive black holes, then they may also be exposed to high-energy radiation that could damage or destroy them. This could affect their suitability as biological materials or their ability to transport them to other places.